Alright, hi year 11, this is Mr. Lim here again, and this is our second video on acids reactions for acids and bases, and it'll go a little bit into all the reactions that you'll have to do in year 12. Let's get started. Right, so we're going to do quite a few different types of reactions, right, more than what we did in year 11. So let's have a go. So ammonia. So ammonia is NH3. Okay, it's a common substance used for cleaning, has the ability to accept a proton in gaseous and aqueous forms, making it a base. Okay, so ammonia and hydrogen chloride gas, that's both of them in gaseous reaction. Gaseous things can react. So if you remember, a limitation of Arrhenius' theory was that it had to be in solution, but Bronsted-Lowry says, okay, well, as long as there's a proton transfer, things should be fine. All right, so this forms ammonium chloride solid, okay? And so what has happened here is that the hydrogen here has been donated to this substance here, forming that NH4 plus effectively, right, in a solid form. And so this what actually happens is that you take two colorless gases, they're not odorless, this one has a pungent smell, and this gas is, very bad for you because, it's acid, right? Take these two gases, and when you mix these two gases together, suddenly an ionic solid will form, and it will form like a white cloudy substance, all right, or cloudy appearance. So that's how this one can react when this one donates a proton to this one. This is an acceptor of a proton, all right, which makes it a base, okay? So ammonia is a weak base, so it only partially ionizes when in solution. So if I have ammonia here as a dissolved aqueous substance in water, right? It's a weak base, so therefore it'll only partially ionize. That's why we got the double arrows, and it'll form NH4 plus AQ and OH minus AQ. Okay, so it will form OH minus ions in solution, all right, but only a few of them, because remember, lots of them will stay as NH3 because they are a weak base. Lots of them will stay this, but only a few of these will form, right? But if you react it with some ethanoic acid, now remember, though, since these are both weak, they stay in their full forms. We put double arrows in. This proton, where this one? Yep. This proton is donated to that substance over there, just like this proton was donated to over here, right? To form NH4 plus AQ and ethanoate ions, CH3COO AQ. All right, so ammonia is again accepting the proton, all right, and turning into ammonium, which is this NH4 plus, right? And since it's a weak substance, it will have the double arrow. You'll notice that this one here doesn't have a double arrow because this one here is a non-reversible reaction, right? This one goes to completion and it stays there because it's hard to break up this ionic solid, right? And then when reacted with an acid, it forms an ammonium salt. So let's have a look. Oh, we just did this one, all right. So this is ammonia with hydrochloric acid. Notice that this is slightly different to the first one because this is in this is in gaseous, this is in solution. So this is NH3AQ plus, now this one here, because it's hydrochloric acid, it's H3O plus. In theory, you know that there is Cl minus ions floating around. Double arrow it. Okay, this hydrogen here is donated to that one there, making NH4 plus H2O plus Cl minus AQ, liquid AQ. So you should recognize that this plus this is the ammonium salt, right? Those two there, right? This is just the water that's there, that's formed, right? But then because this is a spectator ion, you probably wouldn't show that, but you recognize that the salt that is formed is the ammonium chloride salt. All right, so let's move on. Okay, so now we have the ammonium ions and the salts of those ions that are formed by the product of ammonium reactions, and the ammonium ion has the ability to donate a proton and therefore is acidic. So the ammonium ion is this, NH4 plus. So ammonia, NH3, ammonium, NH4 plus. All right, and then this can donate a proton and thus is acidic. So we'll produce the normal acid reaction. So it's an acid reaction. So when it reacts with a hydroxide, it will form water and salt. When it reacts with a carbonate, it will form, carbon dioxide, water, and salt. When it reacts with an acid, it will react and form a hydrogen gas and a salt, but it will also produce some ammonia as well. Okay, it is a weak acid. It will only partially ionize in solution. All right, so let's have a look at some of these reactions. The ammonium chloride in water. So ammonium chloride in water, we're going to say that the ammonium chloride is already split up. Cl minus in water. Okay, this here, the ammonium, is a proton donator, so it's going to take one of those protons and donate it to the water to form, double arrow, H3O plus and Cl minus and NH3. But remember that this is a spectator ion, so you don't really need to show that either. All right, but that's the idea, that there is a proton transfer going across. Okay, next, ammonium chloride solid and sodium hydroxide solid. Okay, so remember that Arrhenius theory could only deal in the solutions, but now the Bronsted-Lowry can do it in other forms. So NH4Cl solid and sodium hydroxide solid. Going to react. Notice it's a single arrow. It's not going to go back because these are solids, right? So therefore, it's going to form NH3, and it's likely to be in gaseous form or slightly in aqueous, depending on how much water is produced, because that's also a product that's produced, and also NaCl solid. Okay, so there has been a proton transfer of a proton from here, transferring to this OH over here. Okay, and therefore it's going to be classified as the acid. Oops, that's not what I wanted. Acid and the base. Okay, so that is a proton transfer in solid form, so that's why we needed the Bronsted-Lowry theory for that. Okay, then ammonium nitrate solution and sodium carbonate solid. Okay, so ammonium nitrate solution. Now, even though it's a weak acid, we do not keep it together, because the part that is weak is the ammonium, not the whole thing, not the molecule. So ammonium nitrate we split up because it's a solution. Sodium carbonate solid we keep together because it's a solid. Whoops, that's what I wanted. Okay, and then this is going to form, right? What is it going to form? It's going to form, because it's an acid plus a carbonate, it's going to form carbon dioxide. It's going to form water. It's going to form the salt, which happens to be Na plus NO3 minus, both of which are always soluble, so we don't need to check for precipitation. And it's also going to form NH3AQ as well. All right, so that's an NH3 on the end. So therefore, this is a spectator ion. Whoops, not that one. That one there. The Na is not a spectator ion because it comes from a solid substance. So that's what you would have after you balanced it with a little bit of this, and a little bit of that, and a little bit of this. Okay? So that's that particular reaction there, where you've got a acid of a proton being donated from this to this CO3, 2 minus, okay? All right, and then finally, let's have a look, ammonium nitrate solution with magnesium oxide solid. Okay, so again, ammonium nitrate. We'll split this up because this is a ionic substance, and then it splits apart, and then the NH4 is the weak acid part. Okay, plus magnesium oxide solid. So magnesium oxide solid. Okay, so you end up with NH3, the ammonia, plus a bit of Mg2 plus AQ, plus a bit of H2O, plus a bit of NO3 minus. Okay, so Water is formed because it's acid plus oxide. Salt is formed, magnesium nitrate. And the additional NH3 is also formed. Right. What can I get rid of as a spectator ion? Only the NO3 minus. Okay, because the magnesium came from a solid form as well, so that one stays there as well. Right. Let's move on. Okay, so oxides of metal and non-metal oxides have different properties. Metal oxides act as bases, while non-metal oxides form acids in solution. Okay, so we've actually dealt with metal oxides before when we deal with acid plus metal oxides, okay, in year 11. But effectively, don't forget that all of these, most of the non-metal oxides are insoluble except for sodium and potassium oxides. When reacted with acids, solid metal oxides will dissolve as the hydrogens are donated to the oxide ion and form water and hydroxide ions. Okay, so I think we just did this one, but we'll do it again. Magnesium oxide, I want that in black. That's not black. Magnesium oxide solid plus hydrochloric acid. So we'll write H3O plus AQ and Cl minus AQ. Okay, goes to, what's that going to form? It's going to dissolve it. It's going to form magnesium 2 plus AQ. And it's also going to form H2O liquid because it's going to be water and the salt of the Cl minus here. Okay, balancing out this equation, you'll need 2 of these, 3 of these, and that's it for the Cl minuses. The Cl minuses get gone because of the what's-majiggy of the spectator ions, okay, and that's it for balancing. All right, so that's how non-metal oxides form, okay. Soluble, what are we doing? Here we go. Soluble oxides of hydroxide form hydroxide ions, so like your sodium oxide and your potassium ions, they form hydroxide ions in water as the oxide ion is too unstable. So sodium oxide in solid in water, so you've got your, whoops, that's not what I want. Oops, that's not what I want. Sodium oxide solid plus a little bit of water. Okay, so that's going to dissolve and form the Na plus O2 minus and 2 of those, right? And some water. This is just showing that it splits, and then it's immediately going to have the hydrogen from the water donate itself to that O2 minus, and you're going to end up with an Na plus, because that's always there. The OH, which is formed from this one, and when this one donates a proton, it also forms another OH. So that's going to form 2 OHs there, right? So the Na plus and the 2 OH minuses are formed, right? And so you end up with, even though it's a sodium oxide, it actually just forms hydroxides there to react with whatever, right? So that's that one there. Okay, and let's move on to the last couple of bits. Right, non-metal oxides will dissolve in water to form acids. Okay, so nitrogen dioxide does something pretty fancy. So when you add it to water, okay, it forms HNO3, nitric acid, and some nitrogen monoxide, okay? So that is going to work if you have 3 of these, okay? Then you have 2 of these, and then you have 1 of the NO, okay? So that is how nitrogen dioxide forms nitric acid and a bit of nitrogen monoxide as well. And then the next reaction for that one would be that the HNO3 then goes with some water and then turns into H3O plus and NO3 minus, okay? So that would form H3O plus ions in solution and therefore form acid in water, right? Next is the sulfur dioxide, so SO2 plus H2O goes to H2SO3, okay, and then the H2SO3 plus a little bit of water will go to, and because this is a weak acid, it will come back as well, to H3O plus HSO3 minus. Okay, right, sulfur trioxide as well will be absorbed in water to form sulfuric acid, and that can be shown in a hydrolysis equation here as well. Right, single arrow because it's a strong acid to form H3O plus HSO4 minus. Right, and then finally carbon dioxide to carbonic acid, and this should hopefully look familiar because it's the same thing that you do when you do the ocean acidification. All right, and then the H2CO3 plus a bit of water, because it's a weak acid, double arrows, H3O plus HCO3 minus. Okay, you can also probably show that these all dissolve in water before they turn into, before you do this particular reaction, like you do for the carbon dioxide, but the idea is that they form acids there. Okay, and then finally, in year 12, the observations for reactions will include the information about which substance is the limiting reagent. Right, this will affect the final appearance of the mixture, as there might be colored ions present or solids still present at the end of the reaction. So, hydrochloric acid with excess magnesium metal, let's write out that equation. Right, hydrochloric acid, because we're using Bronston-Lowry, we're going to write H3O plus because that's what it forms after hydrolysis with water, and a little bit of excess magnesium metal, so you do not need to write out that it's in excess, but you need to know that it's in excess. Okay, then it's going to form H2O liquid, and it's going to form hydrogen gas, and it's going to form Mg2 plus. Okay, going to need two of those, and that will balance out the equation, right? But let's have a look. Because there's excess magnesium metal, there will still be some remaining at the end of the reaction. So your observations will be a colorless solution. That's the hydrochloric acid added to gray solid. That's the magnesium metal, to form a colorless, odorless gas. That's the hydrogen, right? In a colorless solution because the magnesium is not colored. And some gray solid remains. Okay, so you have to indicate that you understand that some of the gray solid will remain, right? Not all of it will dissolve. Okay, next, excess sulfuric acid with calcium carbonate chips. Okay, because it's sulfuric acid, we have H3O plus again because it's a strong acid. Calcium carbonate chips, CaCO3 solid, right? Gonna form some carbon dioxide gas, a little bit of water, a little bit of calcium ions, and I think that's about it. All right, you're gonna need two of those, and two of those, three of those. Okay, yep. So that's now balanced. Okay, so let's write out the reaction. So sulfuric acid, again, all your acids are colorless solutions, unless you add something indicators to it, but we'll get to that later. Right, colorless solutions added to, now this is a white solid because the calcium's not colored, neither is the carbonate. Right, so that's your calcium carbonate to form a colorless, odorless gas. That is the carbon dioxide. A colorless solution. With some white solid. Wait. No white solid remaining because it's got excess acid, which means they're going to all completely run out of the CaCO3. Okay, so therefore you should write out all white solid dissolves. Okay, just to show that you understand which one's in excess. All right, and that's it. Adios.